Hello everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're going to be extending the t-test in two directions. First, the two-sample t-test for comparing means of two independent groups. Second, the paired t-test for data that comes in naturally matched pairs. We're following Bess. She's an investigative journalist on a cold case she can't let go. Today she's covering a story about home prices near a contamination site. An industrial contamination was discovered 18 months ago. One neighborhood sits adjacent to the site, and another comparable neighborhood nearby is unaffected. The story is whether the contamination has measurably suppressed home price growth in the area. To figure this out, she pulls up her case file. The one sample t-test asks whether a sample mean is consistent with a known benchmark. But most real comparisons involve two unknowns. Not does this neighborhood's appreciation match the historical average, but does this neighborhood's appreciation match that other one's? As soon as both sides of the comparison become data instead of a given value, the framework needs to be extended. The two-sample t-test handles exactly that. The null hypothesis is that the two population means are equal. The test statistic is the difference between the two sample means divided by the standard error of that difference. The standard error of the difference combines the uncertainty from both samples. It is the square root of the first group's sample variance divided by its sample size, plus the second group's sample variance divided by its sample size. That structure makes sense if you think about where that uncertainty comes from. Both sample means carry estimation error. Both of those errors contribute to the uncertainty about the difference between them. You add the variance terms and take the square root, the same way you combine independent sources of uncertainty anywhere in statistics. Degrees of freedom for a two-sample test is n1 plus n2 minus 2. The minus 2 here accounts for the fact that you lose 2 degrees of freedom, one for each of the groups that you use in your estimation. Let's go back to the story. Bess pulls 50 recent home sales from each neighborhood. The contaminated neighborhood shows mean annual appreciation of 3% with a sample standard deviation of 5 percentage points. The unaffected neighborhood, however, showed 6% growth with the same standard deviation. The null says that both neighborhoods have the same true appreciation rate, and the alternative here is two-tailed. Since both groups have the same sample size and same sample standard deviation, the standard error simplifies cleanly. It's the square root of 5 squared over 50 plus the square root of 5 squared over 50. Both terms are 0.5, so the standard error is the square root of 1, which is exactly 1 percentage point. The t-statistic is 3 minus 6 divided by 1, which gives us negative 3. Our degrees of freedom are going to be 50 plus 50 minus 2, or 98. With 98 degrees of freedom, and alpha equals 0.05 two-tailed, the critical value is approximately 1.984. Negative 3 clears that easily. She rejects the null. Home price growth in the contaminated neighborhood is significantly lower. Now let's think about the second extension. The two-sample framework requires two groups to be independent. The observations in one group have no natural connection to the observations in the other. But some data does not come that way. Sometimes the same entity gets measured under two different conditions. The same employee before and after a policy change, the same branch before and after a process update, or the same fund months with and without a particular counterparty. When the data comes in matched pairs like that, treating the two groups as independent throws away some useful structure. Here's why it matters. When you compare two independent groups, all the natural variation between units ends up inflating the standard error. That includes differences in seniority between employees, differences in neighborhood quality between properties, anything that makes one observation naturally higher than the other for reasons unrelated to your question. That makes the test less sensitive and obscures the signal that you're trying to find. The paired t-test removes that noise directly. Instead of analyzing two separate groups, you compute the difference within each pair. Each matched pair produces one number, the change for that specific unit. Then you run a one-sample t-test on those differences, testing whether the mean difference is significantly different from 0. The paired structure strips all the between-unit variation that has nothing to do with your question before the test even runs. Bess is investigating a second story. A newsroom recently changed their pay scheme so that their employees get paid partially in company equity. This change was designed to increase the salaries of everyone across the board. Some employees, however, are reporting that they are actually worse off now that the change has been implemented. To figure out what's going on, Bess ends up investigating the 36 different staff positions and how their pay ended up changing before and after the equity pay implementation. So, across the same 36 employees, matched within themselves, she can figure out what the salary looks like before and after the change. She wants to know whether the change produced a statistically significant salary increase on average. she computes the salary difference for each employee. The mean of those 36 differences is positive $2.1 thousand per year. The standard deviation of the differences is $4,200, so the standard error is 4,200 divided by the square root of 36, which ends up giving us exactly $700. The t statistic here is 2,100 divided by 700, giving us 3, and when the degrees of freedom is 36 minus 1, or 35, we end up getting a two-tailed critical value of approximately 2.03 at a confidence level of 95%. A t statistic of 3 clears that comfortably, so she rejects the null. It appears that the change in pay does actually end up improving the pay of the average employee. Notice what the paired structure did for the power of the test. A two-sample test would have treated the two salary columns as coming from independent groups, letting all the variation across all the roles and seniority levels inflate the standard error. The paired approach collapses all of that down to a single column of differences and focuses the test entirely on what actually changed. The question to ask when choosing between the two tests is always, do my observations have a natural one-to-one link across the different conditions? If yes, then compute the differences and run the paired test. If no, then treat the groups as independent and run a standard two-sample test. However, keep in mind that using a two-sample test when the data is paired can potentially end up wasting your power. In her article, Bess explains this to her readers. The neighborhood next to the contamination site is appreciating at half the rate of its comparable, 3 percentage points, 50 sales in each group, and a test statistic that clears the threshold by a mile. The market has already priced in the environmental damage caused by the factory, and it confirms exactly what was found in the environmental report. The pay equity story works the same way, just with a different structure. Because she can match each employee to themselves, she can remove the component of the noise about who earns more for unrelated reasons to the change in the way that they were paid. Bess gets up from her typewriter and goes to investigate her cold case. She's trying to figure out if the hedge fund TRQ was taking advantage of another fund called Callaway Venture Partners. She decides to run a two-sample test, based on Callaway's performance in the months when it didn't trade with TRQ versus the months when it did. What she ends up finding is that they were underperforming by on average 2 percentage points in the months where TRQ was on the other end of the transaction. The t statistic here ends up being negative 2. Checking her critical value, at 95% confidence she gets 2.064, just above her desired confidence threshold. Unfortunately for her, there's not enough evidence for her to prove anything, so she'll have to keep wondering what actually happened between the Rational Quant and Callaway Partners. So that's the two-sample and paired t-tests. The two-sample test compares means from two independent groups with a test statistic equal to the difference in sample means divided by the standard error of that difference. The paired test handles matched data by computing within paired differences first, then running a one-sample t-test on those differences. Pairing removes between unit variation and increases power whenever the natural link between observations is real. The choice between the two comes down to the data structure, independently drawn groups or naturally linked pairs.